Welcome to the MI seminar. So this week we have Wenzer Qin, who's come to us from New York. She's a Simons Junior Fellow at NYU, and I guess split with Flatiron. Is that how?
Sort of, yeah.
Sort of split with Flatiron. And before that, Wenzer did her PhD at MIT. So let's thank Wenzer.
Okay, well, thank you guys for having me. Today I'm going to be telling you about some recent work that we've been titling Not-quite-primordial black holes. In case after this talk you're interested in hearing, seeing any more details about this talk, you can find our work at this archive number here. This is work that I did together with my colleagues Neil Weiner at NYU, as well as Shobhit Kumar, who just started at Tufts as junior faculty, as well as Priya Natarajan at Yale. So just to give you the one-slide summary, I'm going to start by talking about the motivations for this work, and in particular discuss what we know and don't know about the origins of supermassive black holes. And then I'll tell you about this new mechanism where we show that through modest enhancements in dark matter density fluctuations, one may be able to seed supermassive black holes through a mechanism called direct collapse. And then the latter part of this talk, I'll be showing you through some toy model examples how we can produce a sizable population of supermassive black hole seeds, how we might use this to set constraints on different kinds of physics, as well as other implications for particle physics and cosmology. Okay, so just to start, where we got interested in this project, it all really started with the James Webb Space Telescope. And so James Webb launched on Christmas of 2021. And in just a few years that James Webb has been observing, it's seen a number of, let's say, intriguing things. So for example, you may have heard of these so-called little red dots. So this is a population of compact and luminous and red sources that, that people have observed between redshifts about 4 to 9. While their nature is still somewhat uncertain, I think there's been this emerging consensus that they are in fact AGN, perhaps shrouded by some dense star-like envelope. And so that's kind of interesting because at least at first when these came out and people thought they were AGN, there seemed to be some indications that they were perhaps more abundant than people would have naively expected from extrapolating data closer to today to those redshifts. There have also been claims of so-called overmassive black holes. For example, this one that was seen at redshift 10. So here they used both James Webb and Chandra X-ray data and looked at this object. And they tried to measure the mass of the central black hole, as well as the stellar mass of the system. And what they found was that the ratio of the central black hole mass to the stellar mass was nearly 1-to-1. And so if you compare this to our own Milky Way, where the central black hole is a fraction of a percent of the total mass of the galaxy, it really does seem like this black hole is disproportionately large compared to this whole system. There's also this study from last year where they can define a handful of candidate galaxies at these exceedingly high redshifts of 17 and 25. If those were spectroscopically confirmed, those would indeed be probably the very first galaxies we would have expected in our universe's history, at least under a kind of a standard, vanilla cosmology. And then the last study I wanted to mention was this one, where they looked at a black hole inside of one of these little red dots, and they tried to dynamically measure the mass of the black hole by looking at rotation curves. And they found the mass of the black hole to be consistent with about 50 million solar masses. And again, if you compare the mass of the black hole to the stellar mass of the system, they found something that was greater than 2. So again, it seems like this is a really big central black hole, and there are almost no stars in the system. And although we're continuing to sharpen our understanding of what these observations mean, there's at least, it's kind of fun that there's been this tentative evidence that objects in the early universe are perhaps somewhat heavier, perhaps somewhat brighter, or forming in somewhat greater abundances than we would have naively expected. And so I think we've seen, because of this, a revival of interest in the question of how do supermassive black holes form? Just to be very specific, these are the million to billion solar mass black holes that you find at the centers of all galaxies. And the origins of some of these black holes are still rather unknown. And so I think it's interesting to ask, in light of these James Webb observations, do these seem to favor some mechanisms for forming black holes over others? And then since I come from a particle physics background, I think it's fun to ask, are these observations consistent with what we know about standard physics, right? Standard astrophysics, cosmology, or particle physics? And if not, what are the minimal exotic ingredients we can introduce in order to plausibly explain these observations? Okay, so that's kind of the big picture. And now let me tell you a little bit more about what we know and don't know about the formation of supermassive black holes. So typically, mechanisms for forming supermassive black holes get sorted into what are called light seed scenarios and heavy seed scenarios. So how light do I mean by light? Well, at redshift 20, you would expect a light seed to be about 100 solar masses. So this, for example, is what you would expect if you have one of these black holes forming from the very first generation of stars or population 3 stars. The problem is if you take some typical assumptions for how quickly these things can accrete and merge, then it's difficult to explain the largest supermassive black holes that we see today. And so it seems like you may either need to break some of those assumptions or invoke some other way of forming a supermassive black hole seed. And so at least, that's caused people to consider these heavy seed scenarios, where at the same redshift, you would expect these things to be more like 100,000 solar masses. And then the question is, how do you form such a heavy black hole in the first place? And so to my knowledge, the main mechanisms that people discussed in the literature, or at least in the past few years, have been direct collapse black holes as well as primordial black holes. So I'll review both of these for you now. So let's start by talking about direct collapse. And here I'm going to take a rather spherical cow picture for how astrophysical objects form. So first you have to start with some early overdensity. Over time, this overdensity begins to collapse and eventually reaches virial equilibrium, and that's how you get your dark matter halo. So this halo will also contain baryons, and if you want the baryons to be able to continue collapsing to higher densities, right, you need them to fall out of virial equilibrium. So that means there has to be some way for the baryons to dissipate their kinetic energy. In other words, the baryons need to have some kind of cooling mechanism. And so for the very first objects in our universe, before we have things like metals, basically we only have hydrogen and helium sitting around. And so the main cooling mechanisms relevant for the very first objects in our universe are what are called atomic hydrogen cooling and molecular hydrogen cooling, or molecular hydrogen I'll refer to as H2 for short. So the key properties of these cooling mechanisms are that atomic cooling is very efficient for temperatures greater than about 10,000 Kelvin. And moreover, atomic hydrogen is very abundant throughout our universe, right? It makes up like 70-ish% of all matter. Contrast this with molecular cooling, which is efficient down to much lower temperatures, say orders like hundreds of Kelvin. But molecular hydrogen is much less abundant, so whether or not this cooling mechanism is available depends on whether or not you can form enough of it. Okay, so if we want to think about how these two cooling mechanisms affect the formation of the first compact objects, we can look at the Jeans mass. So you may have heard of the Jeans mass as the mass threshold above which the gravity of an object is able to overcome its internal pressures and allow the object to collapse. But in objects, in halos that are larger than the Jeans mass, then what the Jeans mass tells us is approximately the size of the things that form from this collapsing gas. So you can see that the Jeans mass depends on the temperature as t to the 3/2. And so what that means is if both of these cooling mechanisms are available, then because the molecular cooling takes us down to much lower temperatures, you form a relatively small object, for example, a 100 solar mass top 3 star. But if you are able to prevent, somehow suppress the molecular cooling, say you have some extra source that destroys your molecular hydrogen, then you prevent this cooling channel, your temperature stays at a relatively high threshold of 10 to the 4 Kelvin, and you form something that's much larger, say a 100,000 solar mass black hole. So this is the main idea of direct collapse, is if you can suppress the molecular cooling by some method or another, then this leads to the formation of a heavy seed black hole. Okay, so now let's talk about primordial black holes. So here, instead, the only requirement basically to form a primordial black hole is that you have an initial density fluctuation with amplitude greater than about 1/3. And so if we think about the probability distribution of density fluctuations, At the scales where we've been able to measure this, say from the CMB, we know that the typical size of one of those fluctuations is few times 10 to the minus 5. And so if we want this distribution to then have a significant tail that's greater than a third, so that we can form a significant abundance of primordial black holes, we really have to widen this distribution beyond our naive, like what we would have naively extrapolated from the CMB, right? And so you can imagine if you're really widening this distribution of density fluctuations, those big density fluctuations are going to come with other observable consequences. And indeed, people have used these to set all kinds of constraints on primordial black holes. So what I'm showing you now is, as a function of the mass of the black hole, how much we've constrained its abundance, where F here just represents the abundance of the primordial black holes in terms of what fraction of the dark matter they could be. So most people are interested in primordial black holes in that window, because this is still a window where they could possibly make up all of the dark matter. That's not what we're going to be talking about today, since, as I mentioned, we're interested in the seeds of supermassive black holes. We're going to be more interested in this mass range. And so you can see in this mass range, there's already a plethora of different constraints. And in particular, there's this gray one that I'm not sure if you can see in the sliding, but there's this gray one labeled mu that goes all the way down this way. And so I think this is clear to see if we instead of casting this in terms of fraction of dark matter, we cast this in terms of the amplitude of the primordial power that you would need to get that fraction of primordial lines. Yeah, so here I'm now showing the amplitude versus the wave number, which you can map onto the mass of the primordial black hole. And I think this plot is very striking because what these lines are showing here is the level of amplitude you would need in the power spectrum to produce different abundances of primordial black holes. So blue here is what you would need to get primordial black holes making up all of the dark matter. But because these things are forming in the exponential tail of the distribution, you don't need to go down very far before you get this black line, which is 1 part in 10 to the 5 of the dark matter. Gray is 1 part in 10 to the 10 of the dark matter. And then green is 1 primordial black hole per universe. So then the spectral distortions constraint is this red curve here. And so you can see that it rules out even 1 primordial black hole per universe across a large swath of wave numbers and masses. You can get around this somewhat over here by introducing some interesting like non-Gaussian tails to your distribution. But the spectral distortions at least complicate the picture of 10 primordial black holes plausibly serve as a way of seeding supermassive black holes. Okay. So that was kind of the status of things when I started thinking about this topic. And one thing that's always kind of bothered me about this picture, which I mentioned already, is if you're taking this distribution of density fluctuations and really widening it so that you get this tail where you can make primordial black holes, you're also getting all of these density fluctuations that are much bigger than you would have expected from a standard from standard cosmology, but too small to form primordial black holes. And so some people have thought about the consequences of these large density fluctuations already. So for example, if you're familiar at all with the literature on ultra-compact or ultra-dense dark matter halos, that would be a consequence of these large density fluctuations. But I think the baryonic consequences of gas and stuff falling into these upper densities has been somewhat understated, let's say. So let's look into this in detail now. I'm going to start by showing you the evolution of a few different overdensities. So yeah, the amplitude of a dark matter overdensity will be shown on the y-axis here versus redshift. As I mentioned already, sort of from CMB observations, we generally expect the initial value of these overdensities to be few times 10 to the minus 5-ish. So we can take those and we can evolve these in linear perturbation theory. And what that tells us is that during the radiation-dominated era, these things undergo this slow logarithmic growth. And then as they enter into the matter-dominated area, these things begin to grow linearly with redshift. And so I think this is kind of neat because it actually explains why we generally don't expect a lot of structure formation until relatively recently, is because if you start with something that's like 10 to the minus 5-ish, this is just the amount of time or redshift that you would have needed for these overdensities to grow to order 1, right? So within the CDM, all of these modes start collapsing at redshift, let's say 20-ish and later. Okay. Primordial black holes, as we've explained, start off more like order 10 to the -1. And so as these things evolve, they basically instantly enter the nonlinear regime and form your primordial black holes deep into the radiation-dominated era. But now let's consider something more intermediate. Let's take this black curve here and enhance it by a factor of a few times 10. So this thing is going to undergo the same factor of slow logarithmic growth during the radiation-dominated era. But because it still has not gone nonlinear by this point, it's going to continue evolving according to this scaling relation in the matter-dominated era. And so because it's growing linearly with redshift there, what that means is since we've enhanced its amplitude by a few times 10, the point at which this halo form, at which it virializes, is a few times 10 earlier in redshift, right? So if you would have expected this overdensity at this amplitude to collapse by a redshift of 20-ish, now it's collapsing at a redshift of a few hundred. Moreover, since you're collapsing at a redshift of a few hundred, the corresponding dark matter halos are going to be more compact by that factor cubed. And so that's where you get the like ultra dense dark matter halos that I mentioned earlier. Okay, so these things are collapsing at redshift of a few hundred. So what's special about redshift of a few hundred? So here we can turn back to that molecular hydrogen, that molecular cooling picture that I was talking about. And so here's a plot by Chris Harada and Nikhil Padmanabhan, where they looked at the cosmic abundance of molecular hydrogen, or H2, over time. So XH2 here is basically the fraction of total hydrogen in the form of this molecular hydrogen. And so you can see around the time that you would generally expect the first stars to begin forming, the abundance is up here, like 10 to the -6-ish. But then as you go earlier and earlier in time, this abundance falls quite steeply. And that's because at earlier redshifts, the CMB is hot enough to prevent the main pathways by which molecular hydrogen forms. And so that seems kind of interesting because it seems like what this is saying is that molecular cooling is naturally suppressed at very high redshifts. You don't need to add any special ingredients. Okay, but so this is the cosmic abundance of molecular hydrogen. We just want to check that this picture still holds for like the halos, the overdensities collapsing at earlier times that I mentioned, and these will be at much higher densities than like the background cosmic, the cosmic background. So we just want to check that this picture holds inside of an early halo. So we're going to do this through a little time scale argument. And so in order to quantify how much cooling is too much cooling for a halo, in other words, how much molecular cooling would lead to fragmentation instead of the formation of heavy seed, what we can do is compare the molecular cooling time, basically which quantifies how fast the temperature is dropping, to the free fall time of this halo, which just depends on the density of the halo. And so if we plug in typical values for the temperature and densities of the halos that we're concerned with, so this atomic cooling threshold of 10 to the 4 Kelvin, as well as the virial density, which goes as 18 pi squared times the background density. And then we ask, what is the abundance of molecular hydrogen I need to saturate this equality? And what I get is this gray contour here. And so it's kind of interesting that this thing is basically constant across redshift at a fraction of 10 to the -7. And so what that means is if I evolve, let's say, a halo, and I see that it's achieving molecular hydrogen abundances greater than this value, that thing is probably fragmenting. The molecular cooling is efficient in the halo. It's probably fragmenting into smaller things as opposed to forming the large black hole seeds that I care about. Okay. So what we did is we took some toy models for halos. We evolved them as like one-zone halos or spherical top hats, and just evolved their temperature, their density, ionization, and then molecular hydrogen fraction. We evolved them up to the point of virialization, and then basically looked at the final abundance of molecular hydrogen. So these different curves here represent halos that virialize at different times. And so you can see that indeed, as these halos virialize earlier and earlier, the CMB is getting hotter, and that suppresses how much molecular hydrogen you can form in these halos. And so it seems that if you can, if you have these halos forming prior to redshift of 200, definitely, if they're forming prior to redshift of 200, it seems like the molecular hydrogen abundance is sufficiently suppressed that these things act like atomic cooling tanks.
Sorry, you're just stopping that curve at virialization.
Exactly.
That's
Yeah.
what you're doing.
Yes.
Oh, okay, you're gonna cover it. Go.
Yeah. So just to summarize this part, by looking at the cosmic abundance that seemed to imply that you could suppress molecular cooling at early times. We verified this with our spherical top hat halos. I should also mention these couple other works from 2015 and 2024. So here they used more sophisticated codes to evolve halos, but they were concerned with the star-forming properties of these halos. But in the property of studying the star-forming halos, they determined the threshold past which they were like, oh, it seems like these things can't fragment into stars. And they also derived a redshift threshold of about a few hundred. Okay. So it seems like we can get direct collapse for free. Yes.
Yeah, I'll kind of ask my question anyway. So the Harada paper, you remind me that they went through the like old calculations, but then they included something like turbulence or like something with regards to flows between galaxies, which is why they had to revise H2 estimate relative to the old results. And I'm just wondering, is there a relationship between what they were up to there and sort of your halo abundance?
That's a good question. I actually, if you're talking about how they went from like old to new, I actually don't remember. I would have to go back to the paper and figure that out. Okay. Good. So putting everything together, it seems like it ought to be possible to form seeds for supermassive black holes from relatively modest enhancements to density fluctuations. So to make what we've been calling a not-quite-primordial black hole, what you need is for the initial density of one of these overdensities to be large enough so that it collapses prior to redshift of 200, so that for the baryons falling into this halo, molecular cooling is suppressed, as we've seen. Moreover, you need the mass of the halo to be large enough so that as the gas falls into your halo and heats up, it's able to achieve temperatures greater than 10,000 Kelvin, because above that threshold, that's when this atomic cooling is active. So those are the main requirements to form a not-quite-primordial black hole. But now let me tell you about a couple of caveats to this picture. The first one has to do with relative velocities between the dark matter and the baryons. So from this paper by Selyukhovich and Harada in 2010, they reminded us that after baryons decouple from the photons, right, around redshift of 1100, since the baryons have been evolving with the photons and not the dark matter, they're going to have a velocity relative to the dark matter perturbations. And so if you don't account for that, you might predict that structure starts forming earlier than it actually does. So when would this be a problem for our scenario? Well, what you can do is you can take that relative velocity and basically compare it to the gas sound speed in these halos. And if that relative velocity is much higher than the gas sound speed, basically what that's telling you is the baryons are just going to zoom past your dark matter potential and won't be able to fall in. So we want to check when that streaming velocity becomes small enough. Okay. If you look at, different halos, the relative velocity in each of these halos will be different. It'll follow some distribution, but typically the bulk velocity will be about 30 kilometers per second at decoupling, and then that just decays with redshift. Now, the gas sound speed in one of these halos just depends on the temperature. So again, if we plug in that 10,000 Kelvin, what we get is a sound speed of 11 kilometers per second. And so what that means, if we compare these two expressions, is that after redshift of 400, these relative velocities basically become irrelevant for structure formation in our dense halos. That doesn't mean that prior to redshift of 400, you can't form one of these not-quite-primordial black holes, but just the number of halos that have a small enough relative velocity according to this distribution will be small. So if you want to calculate, for example, how many black holes you're getting from this mechanism, you need to account for the fact that fewer of the halos meet the requirements as you go earlier. The other requirement, the other caveat, has to do with angular momentum. So even if you meet all these other conditions for the gas to undergo direct collapse, if the gas has too high of an angular momentum, then it will never be able to overcome the angular momentum barrier to fall into your potential well and rise to higher densities, right? So this was like So this is something that people had to think about when they were first studying direct collapse. And so many of these studies parameterize the angular momentum of these halos in terms of this dimensionless spin parameter, where you take the angular momentum J and you just non-dimensionalize it using the mass of the halo as well as the total energy E. So we took this study from Ladato and Natarajan in 2006, where they found that direct collapse seems to be possible for values of lambda that are less than about 0.02. And so there are a lot of simulation studies that have characterized the spin distribution of halos. And so, for example, there are some that will tell you that at redshift of 10-ish, the spin distribution of halos is very well characterized by a log normal distribution with a width of about 0.04, sorry, with a mean of about 0.04 and then a width of about 0.55. So that's what I'm plotting here. And so if you ask, according to this distribution, how many halos have lambda less than about 0.02, what you get is about 10%. But this is the distribution at redshift of 10, right? And what I've been saying is that we're concerned with halos that might be forming even earlier. So at least according to things like tidal torque theory, the spin distribution of these halos tends to grow with time as they torque on each other. So actually, if you move to earlier redshifts, you would expect that this distribution shifts down, right? So in fact, if we use this distribution, we're being probably a bit too conservative. And in fact, at earlier times, more of our halos will meet the criteria to form a direct collapse black hole. But at least, again, if you want to predict like how many black holes are forming from this mechanism, the angular momentum is something that you want to take into account.
So you're assuming that the baryons inherit the lambda of the
Yes.
halo.
Yeah. I believe I saw some papers by folks like Frank Vandenbosch where they said that this seemed to be the case, that generally the angular momentum of baryons follows the dark matter halos.
And is there still some question about whether how spherically symmetric it is? I mean, you can have something with no angular momentum, but if it's very elongated, it's not going to collapse on a free fall time. It's going to form a filament or a pancake or something. So
I don't quite, sorry, if you don't mind saying that again, I don't quite understand.
well, there's the angular momentum issue, but also whether it's spherical collapse is the right model.
Yeah.
Right, so you have a spherical infall time.
Good. So that's something that we didn't consider for this study. Yeah. I believe that could have an effect, but I don't know how many halos that was. Okay. So again, just to summarize, these are the requirements to get a not-quite-primordial black hole. These are the other things that you may want to take into account when considering actually how many of these halos are able to give rise to not-quite-primordial black holes. And I think another nice way to visualize those requirements is with this contour plot here. So here I'm showing on the y-axis the initial size of a dark matter density perturbation versus its characteristic wave number, which you can map onto the halo mass. And so the black contours here show you, given these numbers, what is the redshift at which you would expect the halo to form. And so as I mentioned, we want these things forming prior to redshift of 200. So that kind of sets this horizontal line here. And then the white contours show you, for the baryons falling into this halo, what is the temperature that the baryons are able to achieve. And as I mentioned, we wanted temperatures greater than 10 to the 4 Kelvin. So that sets this side here. And so what that means is in this pale contour in the upper half of the plot, this is the parameter space where it seems like it ought to be possible to form these not quite primordial black holes. And so if you compare this to the parameter space you needed for PVHs, where the only requirement was that your initial delta be greater than 0.3, it seems like there's a lot more space where you could get halos that form these empty PVHs. And so I think that's really interesting. So now I'm going to talk about broader implications of this and some results. Do people have any questions about the mechanism? Okay, good. Okay, so this is a slide that I added recently because I often get the question of like, okay, what kind of models actually give you enhanced density fluctuations? Why is this interesting to study? And so there are many such models that you find in the particle physics literature. We've already talked about primordial black holes, where you have like a bunch of different inflationary models that will give you all kinds of bumps in your power spectrum. So for example, there's this single field model here by Garcia, Bellido, and Morales, where the engineer some like interesting feature in the inflationary potential, so that as the inflaton traverses this feature, you get this big bump in the power relative to the nearly scale invariant thing you otherwise would have expected from vanilla solar inflation. So there's a single field model. You can also imagine doing this with multi-field models. This is some, I did work on some such models a few years ago. There's a bunch of other funny things you can do with inflation. You can add a spectator field. There's all kinds of models. But you don't have to just do this by altering the initial conditions of the universe. You could imagine that if you have some other interesting cosmologies or alternative dark matter scenarios, you can cause enhancements to basically the growth of the matter perturbations and also stick a bump into your power spectrum. So for example, here I'm showing the Snowmass white paper on cosmic probes of dark matter, where they show the matter power spectrum resulting from a bunch of different models. And you can see here lots of bumps, lots of enhancements from things like if you have some phase of early matter domination, or if you have axion misalignment, etc. So there's lots of models that will lead to enhanced density perturbations. For this first work, we didn't want to cleave too much to any one particular model. We wanted to show that this is a relatively general mechanism that you can get from all kinds of different models. So we're going to, so when we put an enhancement into our power spectrum, we're going to use these narrow peaks or a step function to imitate a model that enhances power across a broader range of scales. Yeah, and so while those are not necessarily the most realistic spectra, it at least shows you that producing these black holes doesn't rely on any one particular model. Okay. So now I'll show you these results in terms of the primordial curvature power spectrum. So here we already see some constraints from, for example, the CMB, as well as the line alpha forest. And then this black line is just, what you get if you take the best fit from the CMB for that, A sub s and n sub s, and then just extrapolate that down to small scales or large wave numbers. We've also talked about constraints from CMB spectral distortions. So these gray contours up here show the constraints from CMB spectral distortions from Kobe virus. That measurement was done 30-ish years ago. And so actually with technology today, if we built a new instrument that could measure the CMB black body, we could potentially be sensitive to the amplitude of the power spectrum all the way down to here. It looks like, an interesting thing is it looks like that this curve doesn't quite touch lambda CDM expectations, but that's actually because when they were making this constraint, they were only considering power spectra in the form of a delta function. They didn't include this scale invariant thing here. And so actually, if you included that, this curve would be able to reach, in fact, what you would expect from lambda CDM. Anyways, one other constraint I wanted to mention is this pink one here. So this is some work by Peter Graham and Hari Krishnan Ranani, where they looked at dynamical heating inside of both galaxies. And so they are able to rule out a little bit more parameter space over in this range here. Okay, so now if I take, again, this power spectrum, and I start sticking, narrow peaks or step functions into it, what we did in this first study is we asked, what is the level of enhancement you need in order to produce enough of these NQPBHs to match, say, the number of density of little red dots as inferred from James Webb observations. And so if that's the question you ask, then what we get is something like this. So if you put a peak at, say, about 100 inverse megaparsecs, then you need to enhance the power spectrum by about 300. If you spread the power across some more scales using something like a step function, then you can reduce this a little bit to an enhancement of about 200. So you can see these are right at the edge of those Ramani and Graham constraints. Whether or not you think this is okay depends on how robust you take their bounds to be. I think there's like a little bit of wiggle room right at the edge here. But so what I think this is interesting because it shows that there is, like, within the allowed parameter space, we can at least produce a significant fraction, right, of the population of supermassive black holes today or at high redshifts. Okay. So hopefully that gives you some idea of like where and how much enhancement you need in order to get a bunch of supermassive black hole states by this mechanism. But you might also be interested in turning this around and asking, okay, well, if some of these power spectra give me too many black holes, can I use this to instead set a constraint on the amplitude of the power spectrum? So we set about to do this in a relatively simple way. So we said, okay, if you have these enhancements in power and the baryons falling into the corresponding orbital densities are forming things like these large black hole seeds, which begin to accrete, or if they fail to form black holes and form things like stars and galaxies at early times, then these things are going to start emitting ionizing radiation much earlier than you would have otherwise expected. And so the simplest models for reionization depend on something called the collapse fraction. So this is just the fraction of all the matter in our universe that has collapsed into halos above some minimum mass at some particular redshift. And so you can calculate this by just integrating all of the mass in the halo mass function above that minimum mass, and then dividing by the mean density of the universe. So the simplest models for reionization that we found said that basically the fraction of our universe that is ionized is proportional to this collapse fraction. And intuitively that makes sense because as you have more structure collapsing, basically you're forming more ionizing sources, and so you'd expect your universe to be more ionized. So then the constant of proportionality here is just telling us how efficient that collapsing matter is, or that collapsed matter is at ionizing the universe. In the literature, you find that this constant of proportionality can span values from like 10 up to hundreds. In order to not set an overly strong constraint, what you want to do is take the smallest reasonable value for this constant of proportionality. So we're going to take 10 since that's about the smallest we found in the literature. Okay, so if you take that thing to be 10, then if you ask, then the universe becomes reionized and the collapse fraction is equal to 0.1, right? And so if you want to set a constraint by asking that the universe not be reionized too early, then you don't want the collapse fraction to hit 0.1 too early. Now we could pick a realistic end for a realistic redshift for the end of reionization. From the CMB, we know that's like 6 or 7. But again, given the simplicity of this model, I worry that choosing a realistic redshift would lead again to a constraint that's too stringent. So what we did is we picked a much earlier redshift. It's like a little bit arbitrary, but I think we can generally agree that the universe should not be reionized by 20. So if you then ask through putting some enhancements in the power spectrum, what's the level of enhancement you need to saturate this limit, then what you get is this purple curve here. So this is where we estimate you would be able to set a constraint on primordial power by asking that the universe not be reionized too early from this early structure formation. There do exist some other constraints in these regions, mostly from properties of dwarf galaxies. We find that this curve is generally competitive with those. But again, this is like a relatively simple thing that we've done. I think it will be interesting to see how this curve shapes up as we use a more realistic model for reionization and then actually compare to data instead of doing this collapse fraction thing that we did. And so I think it'll be interesting to see where that goes. Okay. How am I doing on time?
Got like 15.
Okay, good.
At 1:25, all of the profs will leave to another meeting.
Okay,
You've
so
got 10.
okay. So if you're interested in primordial black holes, I think this has some interesting implications for primordial black holes in a similar mass range. Sometimes when I do this talk, I think it makes people a little bit sad because they start to think, oh my gosh, I can't make primordial black holes in this mass range without way overproducing, supermassive black holes because of these NQPVHs. And that might make us a little bit sad. But I think there's an optimistic take on this, which is that all of these models that gave you PVHs in the supermassive black hole seed range can also give you NQPVHs. And one problem that's faced these models is that in order to get enhancements in the power spectrum that are big enough to give you PVHs, you often had to really fine-tune your model parameters. But since NQPVHs require much more modest enhancements to power, you can really relax the fine-tuning in these models and possibly still create a significant population of supermassive black hole seeds. And so I think that's very exciting, at least. And to show you how this can be done, some people have thought about this already. So for example, some folks have thought about how you can get primordial black holes from, say, a population of cosmic string loops left over in the early universe from some phase transition. And so, for example, my colleague Bryce Sear, who I think some of you know, also wrote a paper, has already written a paper showing how you could seed these not-quite-primordial black holes, but through these cosmic string loops. If you like phase transitions, you can also form primordial black holes from collapsing domain walls. That might be another way you could do this. I also mentioned various models of ultra-slow roll inflation, and this probably also applies to whatever is your favorite model for inflation. Yes.
Quick question. So I mean, yeah, you can directly make the primordial black holes that have collapsing string loops, but then the not quite primordial black holes from cosmic string loops. So that's just an overdensity that then seeds a halo that gives you the not quite primordial black hole.
Yeah, exactly. So, yep. Cool. Other things that we were thinking about. If you have these not quite primordial black holes and these large black holes start to accrete things in the early universe, well, the accretion comes with some amount of radiation, right? And so you can imagine these black holes injecting energy into the universe at these early times more than you would otherwise expect. And so as these black holes radiate, they're going to deposit energy in the form of, say, heating up the surrounding gas, or even ionizing the surrounding gas, etc. So you can see both of those effects here. Here I'm plotting various temperatures as a function of redshift. The matter temperature is this thin gray one. And so you can imagine if I have a bunch of black holes forming in the early universe, you're going to start heating the gas. Similarly here, the black line here is, say, what you would expect for the ionization history within the CDM. Here we see recombination, and then just like the dark ages. But again, if you're putting in a population of accreting black holes, they might start to ionize things early times. So then, so this is, if these effects are in fact there, then you can imagine going and trying and looking for these in various cosmological observations. So for example, if you're really changing the matter temperature, then this is potentially observable in, for example, the 21 centimeter global signal. I'm showing, for example, how that might change the global signal in the form of this black line here. These are preliminary, so don't take these as the quantitative results as too concrete yet. And then also, if you have this big change to the ionization, well, the effect of the ionization history on the CFE has been pretty well studied, particularly in the context of dark matter decay and annihilation. And what we know is that this extra ionization would damp the CMB power spectrum more than we expect. So you could also imagine using the CMB power spectrum to constrain to constrain these not quite primordial black holes, or at least the associated early structure formation. The last follow-up work I wanted to mention is what happens if if your overdensities fail to form the not quite primordial black holes. So as I mentioned, I think just generally the baryonic implications of gas falling into these very complex dark matter halos is very interesting. So it's important to ask, what happens if you don't get the black holes? And if you don't get the black holes, then after redshift of 200 or so, these things are going to begin forming stars. So what do these stellar systems look like today? Well, there's a few things we need to consider when asking what they look like today. For example, if you start forming stars and stars start going supernova, if your dark matter potential well is too shallow, then these supernova are going to blow out all of your gas and stars, and you're not going to have anything. So, for example, what we estimated is this green line here. So this is the level of this is the amplitude of the initial overdensity you would need in order to survive the effect of several supernova in your halo. The other thing that I found really interesting is because if you start at a much larger amplitude, you're going to form a denser halo. Then the stars forming in these systems are also going to be forming at a much higher number density. And if you form at a high enough number density, gravitational scatters between the stars may become efficient, and then you start to get some interesting stellar dynamics. So in a typical galaxy, actually, stars are collisionless. But if you get the stars, if the stars become collisional, they can start to transfer their kinetic energy to the surrounding dark matter halo in such a way that the stars migrate to the center of the potential well to higher densities than you would have expected in a galaxy. So then, for example, what you might expect down here for overdensities that don't survive the effect of supernova is you just get some dark matter halo sitting out there and they eventually get eaten up by a bare dark matter halo. Over here, if you're able to survive the effect of galaxies, but your stars are collisionless, then you might get something that looks like some weird, very early galaxy. But at even higher densities, if you do get this migration effect, such that the stars cluster to the middle and potentially become the dominant components of the gravitational potential, then you'll probably get something that looks more like some kind of interesting early star cluster. So this is also preliminary, but that's generally what we think is going on, what would generally go on inside of these overdensities. Okay, so that brings me to the end of my talk. Just to conclude, not quite primordial black holes. This is a potentially new mechanism for explaining the origin of supermassive black holes that is much less demanding than what you needed for primordial black holes. You can use the associated in early structure formation to set strong constraints on the initial conditions of the universe. And because I think this is a relatively understudied topic, I think there's a lot of interesting future directions we can go. For example, how do these not quite primordial black holes affect cosmological observables due to them dumping extra energy into the universe? And in particular, what happens when you fail to form the not quite primordial black holes in these early overdensities? What other kinds of systems do you get? So yeah, I'll be around for the rest of the day in case you have any more questions. So thank you guys very much.
Next question.
Yes.
So can I ask you about that last point? So in particular, with respect to the angular momentum that you were talking about, or constraints earlier, it was something like, what happens to halo switch failed to form these not quite primordial black holes.
Yeah.
So you said that maybe 90% of them would have too much angular momentum. Right. So what would happen to those halos?
Yeah, so the angular momentum issue is an issue if you want to form a very large object out of this collapsing gas. But if the gas is fragmenting, right, you can imagine there are clumps of gas within the spinning thing, but their individual angular momentum is not large. So eventually you can form stars.
I see. So you would form just a star cluster.
Yeah. Yes.
What can you do with just direct simulations? Can you do a very small cosmological box that has 10 to the 10 solar masses in it and evolve it at a high redshift? So you're not going to evolve it all the way down, obviously. You can only go so far.
Yeah. That is something that I want to do eventually. So we've been talking with, we've tentatively talked about doing this with Sion Zhang, who's a graduating student from Volker Braun's group. That is something I want to do. Just to check that even in a simulation this picture holds. Again, given these arguments, unless there's something missing, I don't see why it wouldn't form in such simulation, but it's always good to check.
Well, it's nonlinear physics.
That's true. That's true.
Right, so everything's just twiddle arguments,
Yes.
but the physics should be pretty clean, right? Because it's pretty simple. Gas dynamics, I would think. Or maybe not.
No, so I agree. So eventually, we do want to follow this up with simulations to see what happens.
They are huge and messy. Some people have done it, right? In the context of just direct black hole formation.
Yeah.
And it's
But it's an isolated system or a cosmological box?
That's a good question. But this is formation.
But you can't, right, so you can't push it to all the way to the black hole. That's resolution isn't going to be there, but you can at least.
Yeah, you do have a scale problem where you're tracking your chemical network, right?
Yeah.
During the dark matter collapse.
Yeah, I think it's you're looking at one system and then they put in some flux of UV photons to destroy the molecular hydrogen. And that's how they study the direct collapse. But yeah, I don't think they go all the way.
And those are few and far between.
But you don't have to, I'm not thinking going all the way to the GR black hole. Just when you start to see highly nonlinear structures and put in a little bump in the power spectrum and then see if you form these structures.
I see, I see. So you want like a cosmological volume.
Cosmological volume,
Mhm.
but it's small. It's not, you're only gonna go to redshift of hundreds or something.
Yeah, I think that would be interesting. Agreed.
Can I ask about your ionization fraction?
Yes,
That looks big.
it is big. So that's why I was like, this is preliminary.
Okay.
So the accretion onto these black holes, the accretion history, the right accretion model to use is still somewhat uncertain. And especially at these, very early redshifts, like accretion might look even more different. So what we're using here is a relatively optimistic accretion model. If you consider something where they accrete much less, you can imagine that this effect would be done.
Because that like Planck would rule that out.
Yeah, right. So you would also be getting concerned about the optical effect. I agree.
Yeah, and just like the tail is going to be flattened, right? You're
The-
rescattering
the
at very
damping.
high redshift,
Yes, yeah,
and
right.
so you're stuck damping tails.
Yeah, so I agree. This one is quite large. We've been toying around with different accretion models that I think will all eventually suppress this.
And can I ask a related question just about the temperature?
Mhm.
I remember there are measurements of the IGM temperature at, redshift.
I think they're a bit later. If you're
They're
looking at the
later.
Lyman alpha, from things from Lyman alpha.
Yeah.
Yeah, so those are like 4 to 6.
Okay.
Which is 4. Yeah, I think 4 to
But then
6.
if I look at your curve, it's diverging like crazy.
Yeah.
Is it gonna cool?
They're as I think as like time goes on and you have more astrophysics, it could cool. Again, we're using the same accretion model
Sure.
as these two things, so this is a very large heating effect. Yeah. At late times, I'm not entirely sure what would
I
happen.
mean, if anything, it seems like a good handle.
I agree. Yes.
So when we were studying this was early on, the density perturbations, and if you just increased it by 10, that changed the line, but you had the matter dominated regime happening around a redshift of 20.
You're talking about here.
Yeah. So
no.
when you're doing the next plot when you had the times 10 version of it.
Yes.
So what you were talking about is these not-quite-primordial black holes, they inject ionization, they do things.
Yeah.
Would that affect where the matter dominated point in the universe would happen? In which case, would that be something we could observe?
I don't think so, because the formation of these things is not going to be significantly impacting the relative abundance, like the cosmic abundance of radiation versus matter. So I don't think it's going to change this time of matter radiation equality, matter radiation equality by very much.
Okay.
And at matter radiation equality, the black holes haven't formed. They're still just like overdensities. Just the overdensities are a bit more evolved, right? Greater amplitude, but they're still matter.